In this video, we are discussing about the photochemistry of dipy method and also the photochemistry of aromatic compounds. So firstly, I am taking the photochemistry of dipy method. It's also called as 1,4-diene, photochemistry of 1,4-diene. 1,4-diene is also called as dipy method. And you can observe that a CH2, 1,4-diene or dipymethane, it's nothing but a derivative of methane. That means divinyl methane. This usually 1,4-diene IUPAC name, and the dipymethane will be the common name and familiar dipymethane rearrangement. You can observe that this is the CH2 and the two olefin or double bonds are there adjacent to the methane. Such compounds undergo dipymethane rearrangement. So here also we can observe that this is the methane and these two are dipy. And this is the methane, these two are dipy. Here in this moiety, two dipymethanes are there. So here I am taking a 1,4-diene, 1,4-diene on irradiation. So it will give you vinyl cyclopropane moiety. Similarly, allyl benzene also undergo dipymethane because this double bond and this double bond are attached to this CH2. So it undergo dipymethane, giving rise to this aromatic compound, cyclopropyl benzene. So let's look into the what are the characteristics of the dipymethane rearrangement. So far, it is possible to do a liquid or solution state rearrangement. That means rearrangement occurs in liquid state as well as solution state. Both singlet and excited states participants. Cyclic 1,4-diene common excited state is triplet. 1,4-diene is unsymmetrical. The reaction intermediate cyclopropyl 1,4 biradical, preferential cleavage towards the unstable radical side. If the 1,4-diene is a part of aromatic ring, regeneration of aromaticity is the product. Dipymethane rearrangement, stereospecific and regio-selective one. So products are cyclopropyl derivatives. Vinyl cyclopropane or aryl cyclopropanes are the compounds. At the termini of 1,4-diene, there is a withdrawing group becomes a part of cyclopropyl ring. If there is a donating group, becomes a part of the olefinic group or unsaturation. So solvents are either alcohols and acetonitrile are used for dipymethane rearrangement. So let's look into the mechanism. So here is the mechanism for 1,4-diene. This 1,4-diene in the ground state, S0 indicates ground state. On irradiation, it will give you the singlet. So when it is singlet, the pi bond, here this pi bond and this pi bond undergo cleavage, so forming a probable bond formation between C2 and C4. That means cyclopropyl moiety is formed, and the obtained one is a 1,4 biradical. This 1,4 biradical are the key intermediates. At this stage, there is a two possibility. The bond breakage between the 2 and 3 are 3 and 4. Okay. If in this case, the bond breakage between the 2 and 3 and the 3 and 4 products are same. But if it is a substituted one, then products will be different. So let us consider that this bond cleaves. If this bond cleaves, then here one radical and here one radical is formed. That's how here radical, and here radical is there, and here already radical is there. So this will give you the picture that there is a formation of cyclopropane ring, and there is a formation of a olefin or double bond between these two carbon. So that is how a cyclopropyl vinyl cyclopropyl compound is obtained. This is also a vinyl cyclopropyl compound. Suppose substituents are different, then here the products are different. But what is common? Cyclopropyl is the common one. I will take one more mechanism. So here I'm taking a allyl benzene. Allyl benzene in ground state and irradiation, it will give you the a singlet one. So singlet one undergoes pi bond cleavage, forming a radical, and in this radical there is a radical at 1 carbon atom, 2 carbon atom, 4 carbon atom, and 5, but there is a bond formation between the 2 and 4, forming an intermediate. This intermediate is called 1,4 biradical intermediate. At this stage, this bond undergo cleavage, so forming a radical here and radical here. That's what I have written here. This clearly indicates that there will be a new pi bond formation between these two carbon and new sigma bond formation between these two carbon. So that is how a cyclopropyl benzene is obtained. Let us take few more examples of dipymethane rearrangement. This also give you the dipymethane rearrangement. This, if we are looking at the mechanism, how this diphenyl, dimethyl 1,4 butadiene 1,4 pentene 1 is irradiated in presence of triplet sensor, gives a cyclopropyl. Cyclopropyl, vinyl cyclopropyl analog or derivative or substituted one. So in the ground state, the substituted 1,4 diene is like this. On irradiation, these two pi bonds undergo cumulative cleavage, forming a 4 radical. Out of 4 radical, these two radical forming a sigma bond, and these two radical will be stabilized. And it's an unsymmetrical one. And then what will happen? There is a cleavage, this bond cleavage. What it means? A sigma CC sigma bond cleavage. That means here one radical is there. So this radical and this radical form a cyclopropane ring, and this radical, newly formed radical and existing radical will form a pi bond. That is how vinyl cyclopropyl moiety is obtained. This is about dipymethane rearrangement. So I'm giving more number of examples of dipymethane rearrangement. So overall, in dipymethane rearrangement, you can remember that two double bonds should be attached to the methyl or methane group. Such compounds undergo dipymethane rearrangement, giving a vinyl cyclopropane as the moiety. And this also dipymethane rearrangement one. So many examples are there, but I'm not taking all those examples. Just I will show you what are the examples of dipymethane rearrangement one. 1 minute. So this is again different one. Okay, this is okay. So here I will show you the few examples of dipymethane. So this is again dipymethane. This is one more dipymethane. This is few more examples of dipymethane. This is again few more examples of dipymethane. These are again few more examples of dipymethane. So what is common? Common is vinyl cyclopropane is common. These are few more dipymethane. This is again, you can also observe that this is the double bond and this is the double bond. This will be the methyl one. So this undergoes dipymethane rearrangement. So giving a bicyclic compound. So here I am taking again one more dipymethane rearrangement. So in this one, this is the CH2. It's not a CH. Even this is one carbon only, okay, but not a CH1. This carbon will have a double bond here and double bond here. That means it undergo cleavage or it undergo dipymethane rearrangement, so giving rise to product. Okay, vinyl cyclopropenyl analog are the products. So with this, I'm taking the photochemistry of aromatic compounds. So aromatic compounds thermally stable, but photochemically highly unstable or labile. So if we are looking at the classification of photochemistry of aromatic compounds, ring isomerization or valence isomerization reactions or products, photocycloadditions of aromatic hydrocarbons, or simple additions of aromatic hydrocarbons, and electrophilic and nucleophilic substitutions of photochemical reactions. These are the types of photochemistry of aromatic compounds. So let us take the first one. You know that benzene. Benzene is the familiar one. And you can also say that it's a Kekulé structure of benzene. So this Kekulé structure of benzene is having the lambda max around 253. When benzene is irradiated with the 253 lambda max, it gives the what are the three compounds? What are the three compounds? At 253, it will give you the two compounds, benzene and fullerene. Okay, but at 160 to 200 nanometer, it will give you benzene, fullerene, and benzene. So these are the three scientists proposed the structure for the benzene initially. So then if we are looking at all these compounds, so what are the compounds? Fullerene and benzene are obtained through benzene. Okay, this benzene, how it is obtained? Benzene is obtained on irradiation of benzene. So let's look into the mechanism. This is the singlet of benzene on irradiation, more particularly at 253 nanometer. Two pi bonds undergo homolytic cleavage, so forming a 4 radicals. Okay, and then there is a bond formation between the first carbon atom and third carbon atom, fourth carbon atom, and second carbon. This is nothing but a structure of benzene. So in the next slide, I'm taking benzene itself. If this benzene undergoes further irradiation, it will give you fullerene. So fullerene, okay, let's take that mechanism. So look here, this is the okay, this on fullerene on irradiation, this is the fullerene, and benzene on irradiation, this bond cleave means homolytic cleavage, forming a radical here. Then this carbon is having a CH1 and hydrogen radical obstruction. So that means this hydrogen radical form a bond with the carbon radical, forming a new carbon radical here, carbon radical here. At this stage, there will be a cleavage, this cyclopropane ring cleavage, and then pi bond cleavage. So giving rise to a radical, 6 radical. Here one radical, 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 here one radical. So totally a structure of fullerene moiety. And then benzene formation by benzene itself. Let's take the benzene. So a ground state one. This on irradiation with the 160 to 200 nanometer, it will give you the singlet and singlet 1 and singlet 2. Later on, there will be a cleavage, pi bond cleavage. So giving rise to a 4 electron or 4 radical, and these two two second radical and third radical form a bond. 1,4 radical will form a bond. So giving rise to Dewar structure. This is also possible. Singlet 2 can be converted into singlet 1. Singlet 1 can transfer to a triplet 1, and triplet 1 can give you the Dewar's structure. And this can form a bond giving rise to Dewar structure. So I'm taking the substituted benzene. So substituted benzene on irradiation, it will give you, if 1,2 disubstituted benzene on irradiation, it will give you 1,3 disubstituted benzene. 1,2 irradiation gives 1,3 disubstituted 1 through benzene intermediate. I will go to the next slide. In the next slide, I am taking 1, 3, 5 methyl benzene. Okay, polybenzene on irradiation, it will give you 1, 2, 4 trimethyl benzene. Irradiation with the sunlight or photochemical source, so forming an intermediate, a benzene is obtained. The bis benzene is converted into this form. So here I am taking few more examples. Alkene is added to the what you call benzene at 1, 2 or 1, 3. It will give you different products. So ortho attack a cyclobutanone 1, meta attack a tricyclic moiety, and para attack a bicyclic moiety is obtained. Then a few more examples of addition of double bond to a benzene. More particularly here the mechanism is discussed. That means these two pi bond cleavage, so forming a bond and leaving behind the radical at the second position and the fourth carbon atom. So forming a cyclopropane ring and giving rise to this product. I will take the mechanism, another 2 pi plus 2 pi mechanism, that is benzene when it is treated with an alkene, dimethoxyalkene. So it will give you the cyclopropane benzene 1. Cyclopropane benzene 1 undergoes electrocyclic ring opening, so forming this compound. And then similarly, benzene on reaction with the acetylene, giving rise to bicyclic moiety, and this undergo electrocyclic ring opening, forming a compound. Then this is again one more example, more particularly para attack 1. Then here I am taking few more examples: endo product, regioselective 1, and mixture of compound. If it is electron withdrawing is attached, that means acrylonitrile 1. So exo and endo. Endo will be the major one because it will have interaction with the existing pi bond, but obtained product according to photochemical condition is 1:1. And here only one product is formed with respect to acetyl ethene, acetoxy-vinyl, methoxy benzene. Methoxyalkene also gives you selectively one product. So then 2 plus 2 addition 1, a cyclopropane ring formation between this carbon and this carbon, forming a product, and the ring junction is cis, means less than 5 number substitute reactant. Cyclopropane ring means it is a cis one. Suppose a 6-membered ring is formed means then it is a trans-cis possible. This is also a cis one is possible. And then this is the one more. Then a simple addition, more particularly the role of amines in the photochemistry of benzene. You know that a triethylamine and the benzene on irradiation, it will give you biphenyl. So tetrahydrobiphenyl are the products. In addition to that, one more product, one more byproduct. You can say that methyl amine tetrahydrobenzene. So let's look into the mechanism. The benzene undergoes homolytic cleavage, so forming a radical. Okay, one radical here, one radical here, and then one of the radical from the nitrogen is given to the carbon, forming a carbanion. So this carbanion can obstruct a proton from this amine source intermediate, so forming an alkene and dihydrobenzene. So this dihydrobenzene can undergo 1,3 hydrogen shift, so forming a compound. Then obtained one react with the radical. Obtained with the radical, forming a compound like this. And then with this, I will go to the next slide. Next slide, how a biphenyl tetrahydrobiphenyl is formed. That mechanism I am discussing. Here you can observe that singlet benzene undergo reaction with the triethylamine, forming a radical on this carbon and then radical on that carbon. And then this electron can transfer here, then anion is obtained. Then what will happen? This anion form a double bond here, and this double bond can sit as a anion one. At this stage, this anion captures the proton, and this bond pair is forming. So now the obtained one is a radical, tetrahydro radical. This tetrahydro radical undergoes dimerization, forming a tetrahydro biphenyl compound. Similarly, benzene and reaction with pyrrole on irradiation, it will give you an intermediate. Later on, it will give you a two tetrahydrophenyl. Pyrrole is the product. So let us take the electrophilic and nucleophilic additions of photochemistry of aromatic benzene. So here I'm taking deuterated methoxybenzene. This on irradiation with trifluoroacetic acid, it will give you anisole. Similarly, benzene in the ground state and reaction with malic halide, right? At 290 nanometer irradiation, it will give you 2-phenyl, okay? 2-phenyl malic halide, right? So if we are looking at the mechanism, ground state benzene react with the excited state malic anhydride, gives a singlet one. Singlet crosses the intersystem crossing and then react with the malic anhydride, forming an intermediate, and then finally it will give you the product with the loss of hydrogen. Then here I am taking more common nucleophilic substitution reaction. So here the living group is methoxy. Methoxy is replaced with cyano. And in this one also, so chlorine is the living group. Chlorine is replaced with the cyano. And in this one, cyanation occurs. Cyano is added to fourth position. Next, I'm taking two more examples. So here I'm taking a methoxy mechanism of the previous reaction, that is the ground state anisole. On irradiation, it will goes to a singlet. Singlet one crosses the intersystem crossing, forming a anisole. This anisole on reaction with the electron, then the obtained one is a positive charge on the this carbon, and here proton obstruction. Then since there is a positive charge, Cn minus will attack here, forming a radical on this, then hydrogen radical obstruction, forming a compound. Later on, H minus removal, giving rise to product. Then here I am taking few more examples of nucleophilic substitution reaction. So what is here? A methoxy group is replaced with the primary methylamine. Similarly, a methoxy group is replaced with the methylamine, and methoxy group is replaced with the OH minus means hydroxyl anion. Similarly, a pentachlorophenol on irradiation with a, photochemical source with the OH minus, then it is observed that a metachloro is replaced with OH minus. Similarly, one more example, methoxy group is replaced with amide. So this is about what is called as dipymethane rearrangement mechanism and example, and photochemistry of aromatic compounds. Photochemistry of aromatic compounds, under that how the divar benzene, fullerene benzene, and benzylene benzene is obtained, and simple addition reactions, and electrophilic, less common electrophilic reactions, and the more common nucleophilic reactions. So with this, I will stop at this stage and will continue in the next class.